Well, hello and welcome to the 27th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. So, we were in the process of obtaining the most powerful unfalsified model for a given trajectory data set. So, what was our data set? D is given by W0, W1, W2 dot dot dot. Yeah, this is a trajectory of a dynamical system which is expectedly coming from a behavior which is given by the kernel of a polynomial matrix. The idea is to find out the kernel representation matrix R sigma, which describes in B in such a way that it allows only minimal extra information that can be got from this behavior B. That means the tightest possible behavior that explains this data, right. We looked at a scalar example and we found out that a very nice and convenient way of finding out equations that are unfalsified by the data. That means equations that this data will satisfy, polynomial equations, difference equations, is by looking at its various Hankel matrices H, K, W, which is defined as W0, W1, W2 dot dot dot, W1, W2, W3 dot dot dot, W2, W3, W4 dot dot dot, dot dot dot, WK, WK plus 1 dot dot dot, WK plus 2 dot dot dot. So, it is an infinite number of columns and k plus 1 times q number of rows, such a matrix, and finding out left kernels of these Hankel matrices is the key towards obtaining these equations which are unfalsified by the data. In fact, left kernel of the kth Hankel matrix is in fact equal to the annihilating polynomial row vectors of the data whose degrees are less than or equal to k. Let me explain. This n is the collection of all R psi 1 cross q psi such that R sigma W is equal to 0. That is the annihilating module of the data, In fact, identifying this annihilating module is what our job is after all, because once we obtain this annihilator, right, we know that we have seen this row module one to one correspondence. So, we look at the trajectory, the most powerful unfalsified model is the smallest behavior, right, that contains the data. Okay. So, now what we want to obtain is find out the module corresponding to that behavior, and that module corresponding to the behavior is the annihilating module that annihilates this data, which also would mean that it annihilates that smallest behavior. So, in fact, it is identifying this annihilator is what we are in fact ultimately after, right. But how do we get this annihilating module of the data? So, first we notice that the annihilating module of the data, what we have seen in the other lecture in the last lecture, is that if I now define that nk is by definition the collection of all those R psi which is an annihilator and has the property that its degree is less than or equal to k. If that is nk, then it follows that left kernel of the Hankel matrix, the kth Hankel matrix, is in one-to-one correspondence. So, that is why I am writing equal under the identification of these vectors, the vectors in the left kernel of this matrix of size 1 cross k plus 1 times q. If you identify those row vectors with polynomial row vectors like the way we did, then under the identification we have this equality, correct. Now, the thing is that if we are after all possible annihilators of all possible degrees, then it appears as if I have to look for this left kernel for all values of k starting from k equal to 0, 1, 2, 3, 4, 5. I have to continue forever because I do not know what is the degree of these annihilators. You know, annihilators can be of as high degree as possible, yeah, as you want. Like for example, think of this sigma minus 1, just simple equation w equal to 0, that was let us say a behavior which was generating the data, and we have seen the kind of data that it generates. What is the largest degree of annihilating polynomial that is possible? Is it possible to have a quadratic polynomial that will annihilate this polynomial, annihilate this trajectory? Of course, you know, I just take sigma square minus 1. Yeah. Is it possible to have a polynomial of degree 5? Of course, sigma to the power 5 minus 1. Is it possible to have a polynomial of degree 1 million? Of course, sigma to the power 1 million, I think 10 to the power 5, 10 to the power 6, sorry, 10 to the power 6, 1 million, 10 to the power 6 minus 1 w, that also is okay. Can you tell me why all these degrees are possible? Because all of these degrees will have sigma minus 1 as a factor. The moment you have sigma minus 1 as a factor, and if you know that your trajectory satisfies this, then the trajectory will satisfy all the other guys as well. So, although the degrees of these annihilating polynomials can be as high as possible, it seems likely that those high degree polynomials perhaps are coming from some smaller degree polynomials, you know, some multiples of some smaller degree polynomials. Okay. But how to find out those smaller degree polynomials which will describe the system, you know, so that every other equation is also obtainable? Is it really possible to get that from by looking at the left kernel of these Hankel matrices? Okay. Right. So, how do you get this? How do you get this annihilating module? So, the equations by looking at these hk, is it really possible to do that without going on forever? Okay. That will require us to find out certain properties about these Hankel matrices. So, first thing that we notice is the following. We may assume without loss of generality that H0k has no H0w has no relation among its rows. Yeah, that would mean that there are some 0th order equations. There could be, but it is safe to assume that such things are not there. So, we are assuming that there are no constant equations that these guys satisfy. They satisfy only polynomial difference equations. Now, so this is then full rank. So, what we are going to ask is the rank of these Hankel matrices one after the other. So, what is the rank of this guy? We call it, we give it a name, we call it D0, and it turns out that we can assume without loss of generality that this is Q. That is the number of variables that are there in each of these vectors, okay, number of entries in these vectors. So, this is Q. Now, I look at what is the rank of the first Hankel matrix. I give it a name D1, and what is this value? Can we say something about D1 and D0? Notice that this rank I can get some upper bounds. The D1 rank is less than or equal to 2q. Why is that so? Why is that so? because how many rows does this matrix has does this matrix have? It is H1 W is W0, W1, W2, so on, then W1, W2, W3, so on. So it has 2q number of rows. So the for such things that row rank is equal to column rank. So rank is equal to row rank, and because there are 2q number of rows, the row rank can never be bigger than or equal to bigger than 2q. It can at most be 2q. So that is why the rank of H1W, which is D1, is less than or equal to 2q, correct. But now notice the following, because I have assumed that rank of H0 is q. So that means these rows in H1 are linearly independent. So the rank will have to be bigger than this q, because new rows are being added. It may turn out that all of them are dependent on each other, but there could be more rows as well, but I know at least q number of rows are linearly independent. So what I am trying to say here is that it would mean D1 must be bigger than or equal to D0, isn't it? Okay. So here is the thing, I know for sure that D0 is less than or equal to D1. Okay. Let me write it a little bigger as well. D0 is, sorry, wrong direction, is bigger, oh sorry, my bad, it was correct the other way around. D0 is less than or equal to D1. Now let me ask the question, same question for H2. H2W, what is this? H2W is W0, W1, W2, W3, so on, W1, W2, W3, W4, dot dot dot, W2, W3, W4, W5, dot dot dot, and so on. So you see H1 is already a part of H2, correct. So those linearly independent rows in H1, whatever they were, and I know that there were D1 of them, D1 such linearly independent rows are there, and now few new rows have been added. So the rank can only increase. So rank of H2, which is D2, will then be bigger than or equal to D1, because H1 W is already a part of H2W, because it is already a part, it is a sub matrix. Those linearly independent rows will continue to be linearly independent in H2, but there could still be more rows, therefore D2 must be bigger than or equal to D1. So I have this, and you see this trend will obviously continue, you can just verify yourself, and this is what we have. But this is trivial, we have not done much thinking, but notice that this thing, but this is important. So that is why I am calling it 1. Now I am going to define the following, I am going to define rho k to be equal to dk minus dk minus 1. Okay. What does this mean? This means this is a change in dimension, how much the dimension is increasing. So rank of Hk and rank of Hk minus 1, how much the rank has changed from between Hk minus 1 and Hk. That is the question that we are asking, and that is what we are defining as rho k. But this also necessitates us to define what is rho 0, because d minus 1 we have not defined. So rho 0 we define to be equal to d0. Now something funny will happen about this rho case. What can we say about rho 0 and rho 1? Which one is bigger, which one is smaller? let us try and investigate. Let us look at H 0 and H 1. I just need to look at H 1. Okay. H 1 is W 0, W 1, W 2, W 1, W 2, W 3. What is rho 0? Remember, rho 0 is D 0, which we have assumed to be equal to Q. What is rho 1? Rho 1 is the difference between D 1 and D 0. So, how much the dimension has increased? What is, by how much can it increase? It can increase only by Q, not more than that. Can it increase more than Q? Of course not, because then the rank will be more than 2 Q, no, but the rank cannot be more than 2 Q. So, at most it would have increased by Q, it will increase by Q or less, because that is the number of rows that we have added. So, rho 1 is at most Q, not more than that, which then immediately means that rho 0 must be bigger than or equal to rho 1, because rho 0 is just Q, very simple. So, that is the inequality. Now, we ask this question, that what is rho 2, what is the relation between rho 1 and rho 2? I say the trend will continue, it will be like this, not just that, it will be like this, 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 and so on, it will continue. This will be our number 2 observation, but this is, but why is this so? That is a really non-trivial thing, and that is what we need to understand in a bit more detail, a bit more carefully. So, for that I am going to first write H 2, and then I will try to argue out why should rho 2 be less than or equal to rho 1. Notice carefully, this is going to be very important for us. W 0, W 1, W 2, W 3 dot dot dot, W 1, W 2, W 3, W 4 dot dot dot, W 2, W 3, W 4, W 5 dot dot dot, like this. Okay. Now, so when is rho 1 strictly less than rho 0, which is equal to Q? This happens when there are some first order relations, is not it? You get rho 1 to be strictly less than rho 0, that means Q. So, you have added Q new rows, but you have not added rank as much. The rank has not increased by Q, the rank is less than the number of extra rows that you have added. That means, these rows must have been dependent. Yeah, overall there are dependents on these rows, not 2 Q number of rows are independent. And when these 2 Q number of rows are not independent, that means the left kernel of H 1 W is non-trivial. So, you have vectors in the left kernel. Suppose you have a vector R 0 R 1, which is in the left kernel, is a non-zero vector in the left kernel of H 1, and that is what has caused the rank to drop from the possible 2 Q value, and it is strictly less than 2 Q, and that has happened precisely because there is this non-zero row vector R 0 R 1 in the left kernel of H 1. Okay. Now, notice the following: if R 0 R 1 is in the left kernel of was it H 1? Yeah, I think it was H 1. Yeah, it is in the H 1 of W, then this immediately means that 0 Q number of them R 0 R 1 is automatically in the left kernel of H 2 W. That is surprising, is not it? But think about it, look at this matrix H 2 W. R 0 R 1 in the left kernel of H 1 would mean R 0 W 0 plus R 1 W 1 is equal to 0, R 0 W 1 plus R 2 sorry R 1, I should not do this, R 1 W 2 is equal to 0. In fact, continued like this, we actually have R 0 W k plus R 1 W k plus 1 is equal to 0 for all k. Yeah, but then that means what? If I now look at let me just get rid of this and write it like this. Now, if I look at 0 q number of them, R 0 and R 1, I put them like this, q q, then this row vector multiplied by this infinitely many column size column vector gives me R 0 W 1 plus R 1 W 2, but that is equal to 0. You see, not just that, second thing is R 0 W 2 plus R 1 W 3, that also is equal to 0, because you see this is the general equation that has to be satisfied. So, in fact, 0 R 0 R 1 tells me that this is, because this is true for all k, especially if k is equal to 1 2 3 4, yeah, 1 2 3 4, as opposed to starting from 0 1 2. If it is 1 2 3 4, it says that this 0 R 0 R 1 times this thing is also equal to 0, which means 0 R 0 R 1 is in the left kernel of H 2, correct. And this is for all, in fact, for every vector R, for every vector R in left kernel of H 1 W, we have that the shifted version of that is in the left kernel of H 2 W, which then means essentially is that when I was counting down my rows, I had some independent rows, all right, but there were some dependent rows as well, some rows that are involved in this linear combination business. Those corresponding rows here will continue to be dependent, yeah, because now R 0 R 0 R 1, same equations, just shifted version of them will also be satisfied. So, that means these new q rows that I have added, out of those new q rows, how much ever was taken away by the first order equations will continue to be taken away by the second order equations as well, which are the shifted versions of my first order equations. So, what was that number? Row 1 number of independent rows I have added, yeah. So, q minus row 1 such rows actually had turned out to be linearly dependent. So, same q minus row 1 number of rows will continue to be linearly dependent on these on the previous guys. So, that many rows I will I will be able to add independent rows only row 1 number of them, yeah, but perhaps there will be still further second order equations which are not shifted versions of them, correct, and those those will correspond to after those new second order equations are taken away, those rows are taken away, those rows are dependent, the remaining rows will contribute towards the increment of the rank of the Hankel matrix, isn't it, which then means that row 2 can only be at most equal to row 1, but not more than that. Okay. Yeah, I hope you understood what is going on. If not, then go back, do a rewind and listen to it again. All we are saying is that because of this very interesting fact that whenever I have something in the in the left kernel of H1, a shifted version of that will automatically be in the left kernel of H2. So, therefore, the dependent rows that were there in H1, the corresponding rows that you get in H2, they are the shifted versions of, they are the shifted versions of rows in H1. Yeah, that's what come that's what come in H2. So, those corresponding rows will continue to be linearly dependent because of this shifted version thing, and therefore, those many, at least those many dependency, that much of dependency will already be there. Still further new dependency might arise, which will cut down on the increment of the rank by even more. So, that is why the rank increment can be at most row 1, but it could still be less than row 1. So, that is why it is row 2 is less than or equal to row 1, and this idea will continue. This idea will continue. That is why our number 2 has, number 2 observation has this continued calculation, this continued analysis. You see, row 1 is bigger than or equal to row 2, row 3 is bigger than or equal to row 2, row 4 is bigger than or equal, sorry, row 3 is bigger than or equal to row 4. It is a decrease, it is a non-increasing sequence. Non-increasing sequence. If it is a non-increasing sequence, then something interesting can be said about this. You see, because it is a non-increasing sequence, this will exist, limit k tending to infinity, rho k will be some rho infinity. This limit will exist. Why? Because these rho k's are all non-negative integers, right, because they are defined as dk minus 1, and dk is bigger than or equal to dk minus 1. So, these are non-negative numbers and they are decreasing or rather non-increasing. So, can they go on forever? They start from some number, isn't it? They start from some non-negative number, and then either they remain same or they decrease, or remain same or decrease. Can they keep on decreasing forever? They have to saturate at one point of time, and that is why the limit will always exist. But the existence of the limit has a funny consequence. The existence of the limit, if I now find out a capital K, or rather should I call it capital T, I think better to call it capital T, or say capital K is also fine. So, capital K, if I find out a capital K, which is a positive or rather non-negative integer, such that this is the first time for which such that for all small k bigger than or equal to capital K, we have rho k plus 1 is equal to rho k. It will turn out that for any small k bigger than or equal to capital K, if you go up to that k, do this and find out the left kernel of this Hankel matrix, yeah, that will give us the equation that we wanted. Yeah, this left kernel, which will give us some polynomial matrix, right. So, that polynomial matrix is the one that will give us the most powerful unfalsified model for this given situation, yeah, for this given data set, given trajectory data set. Now, why is that so? See, remember, let me repeat what I just mentioned. So, first thing, we notice because of this shifting property that the rank of the Hankel matrix must be such that its increment, the rate of its increment will saturate. It cannot increase, it cannot sustain its rank increment forever. It has to saturate at some point of time. The rank might not saturate, the rank might not become fixed, the rank might still keep on increasing, but the rate of change of its increase will saturate. Yeah, this row vector, these row numbers will these numbers rho, they will saturate. That means there will come a stage that when you go from kth Hankel matrix to the k plus first Hankel matrix, the rank change that will be there, same rank change will happen when you go from k plus first Hankel matrix to k plus second Hankel matrix. The same rank increment will be there when you go from k plus second Hankel matrix to the k plus third Hankel matrix, and this will continue forever. The rank will keep on increasing only by a fixed amount, right. That is the saturation point. Now, you take a Hankel matrix of size of these, of the, so you take a kth Hankel matrix where k is bigger than or equal to this saturation point. Now, look at that Hankel matrix and find out its left kernel. That will give you some polynomial row vectors. Yeah, collect these polynomial row vectors. That is your most powerful unfalsified model of the given data set. Yeah. How do you prove this? To understand this, we need to understand what is happening to these left kernels as well. Yeah, how their rank, how their dimension, the dimension of these left kernels are increasing. Yeah, and what property do they satisfy? And what it means to have this saturation occurring. When this saturation occurs, what happens to the left kernels, to the dimension of the left kernels? The answer to these questions will tell us, will finally lead us to the fact that if I go beyond the saturation point and take a Hankel matrix there and find out its left kernel, that is the most powerful unfalsified model for us. Yeah, a solution, an answer to this mystery and many more such things is what we are going to see in the next few lectures. Till then, take care of yourselves. Bye.